Today, we are glad to introduce our paper, RankTower, a synergistic framework for enhancing two-tower pre-ranking model. We will begin with a brief introduction to the problem context and the pre-ranking aspect, followed by an introduction of our proposed model architecture and optimization. Finally, we will discuss the designed experiments to better understand our model's performance and characteristics. In industry, the cascading architecture ranking system has been widely used to achieve a balance between efficiency and effectiveness. A typical cascade ranking system consists of multiple sequential stages, including recall, pre-ranking, ranking, and re-ranking stages. Pre-ranking is commonly regarded as a lightweight ranking module characterized by a simpler network architecture and a reduced set of features. Compared to ranking models, pre-ranking models are required to score a larger number of candidate items for each user and demonstrate higher inference efficiency. In this paper, we propose a novel pre-ranking framework called RankTower to address these challenges. The primary contributions are as follows. We introduce the RankTower architecture. This architecture efficiently captures user-item interactions while following the user-item decoupling paradigm to ensure online inference efficiency. We employ a full-stage sampling strategy by drawing the training samples from different stages of the cascade ranking system. Tightly coupled with this sampling approach, we strategically integrate a hybrid loss function that combines distillation and learning to rank losses. This synergistic approach facilitates comprehensive learning of the ordering dynamics underlying user interactions while aligning with the inherent patterns of the cascade ranking system. Experiments on public datasets demonstrate that RankTower significantly outperforms state-of-the-art pre-ranking models in terms of prediction accuracy and inference efficiency. The RankTower architecture mainly consists of three main modules: multi-head gated network for computing diversified user and item representations, gated cross-attention network for modeling bidirectional user-item interactions, and maximum similarity layer for efficiently capturing user-item interactions to compute the final prediction. RankTower follows the user-item decoupling paradigm, enabling efficient online serving by pre-computing and caching user and item embeddings. During online serving, only the gated cross-attention layers require forward propagation, while other operations remain parameter-free, optimizing computational efficiency. The multi-head gated network is an enhanced MLP augmented with a gating mechanism for extracting diverse user and item representations. The MLP output is multiplied by an instance-aware gating vector, modeled by a two-layer MLP. The input embedding does not receive gradients from the gating network during training for stability. The gated cross-attention network employs the cross-attention mechanism to effectively model the interaction between user embedding and item embedding. It utilizes the gated attention unit as the main building block, along with residual connections and layer normalization for training stability. This cross-attention mechanism with two parallel branches is designed to simultaneously attend to both user preferences and item characteristics. The maximum similarity layer computes the final probability prediction based on the user and item-attended embeddings. Specifically, each user subspace computes the maximum cosine similarity with all item subspaces, and the scalar outputs are summed across user subspaces. And we have a learnable temperature scaler for rescaling the cosine similarity. Note that the maximum similarity layer does not have any parameters, which is suitable for online serving. Now we will give a detailed introduction about outmodels training and optimization strategy. The pre-ranking model, which operates on the outputs of recall models, aims to identify the most relevant candidates set for the ranking model. Consequently, aligning the item distribution between the training and serving phases is essential to mitigate this sample selection bias and improve model effectiveness. We implemented full-stage sampling to draw training data from impression samples, candidate samples, and random samples to mitigate sample selection bias. The impression samples are items output by the ranking model and viewed by the user consist of both positive and negative samples. Positive samples are items that have received various types of positive user feedback, while negative samples are items that have been exposed to the user without receiving user feedback. The candidate samples are items in the ranking or pre-ranking stages that are not viewed by the user are categorized based on their progression through the cascade ranking pipeline. Ranking candidates, which have advanced to the ranking stage, are generally considered as hard negative samples due to their higher relevance and quality compared to the pre-ranking candidates. Pre-ranking candidates are regarded as relatively easy negative samples because they were filtered out before reaching the ranking stage. The random samples are items that are randomly sampled from the item corpus to serve as negative samples. These random samples are considered the easiest negative samples, but are included to further enhance the generalization capability of the pre-ranking model. For labels, our framework incorporates two types of labels, hard labels and soft labels. Hard labels represent various types of positive user feedback on impression samples, while soft labels are predictions made by the ranking models, used knowledge distillation. Both categories of labels require an aggregation function to consolidate the different user behaviors into a single scalar value for the pre-ranking model's learning. The aggregation of hard labels is highly dependent on the specific business problem, requiring that labels be aggregated according to their orders of importance. For soft labels, we use the ranking objective function as aggregation function. This approach ensures that the soft labels are seamlessly integrated into the training process, maintaining the consistency between the pre-ranking model and the ranking model. For loss functions, our framework utilizes three different losses for training the model. The distillation loss is utilized for distilling the knowledge from ranking model. As the main goal for the pre-ranking model is to output a high-quality item set for the ranking model, hence we used a listwise loss for distilling the knowledge from the ranking model. The fine-grained ranking loss is applied to both impression and candidate samples, which directly correspond to the sample scope used in serving. We employ the soft sort, a differentiable sorting loss, to learn user behavior and the patterns of the cascade ranking system. This loss function aims to precisely rank items according to the varying degrees of positive feedback they receive and effectively differentiate positives from impression samples and negatives from candidate samples. The coarse-grained ranking loss, applied to all samples, aims to separate positive and negative samples while supporting ranking among positives by distinguishing varying degrees of relevance. We propose the adaptive margin rank max loss, an extension of the rank max loss that introduces an adaptive margin based on the pair's nature and label distance, thereby extending the rank max loss to address ranking problems with ordered or continuous positive labels. We design a hybrid ranking loss that integrates both distillation and ranking objectives. Balancing distillation and ranking losses is crucial for the pre-ranking model to inherit the ranking model's capabilities while generalizing to broader sample spaces. Weighting fine-grained and coarse-grained ranking losses ensures a balance between precise ranking and overall retrieval robustness. Our synergistic framework is designed to learn both the hierarchy of user behaviors and the pattern of the cascade ranking system. We conduct experiments on 3 large-scale public datasets from online advertising, e-commerce, and short video recommendation domains to evaluate the effectiveness of RankTower. We can see that the RankTower achieves the best prediction performance, attributed to its effective modeling of bidirectional user item feature interactions and the design of full-stage sampling and hybrid loss functions. To gain deeper insights into the proposed model, we conduct experiments on the Quairan dataset and compare model performance on different settings, including 1. The effect of full-stage data sampling, 2. The effect of listwise ranking losses, and 3. The effect of distillation from the ranking model. For the effect of full-stage sampling, we conduct an ablation study to evaluate the impact of each sampling component on the model's performance. The full-stage sampling strategy achieves the best overall performance. Training the pre-ranking model solely with impression samples hinders its ability to generalize to unexposed items, negatively affecting retrieval performance. We also observe that candidate samples are more important than random samples, as they significantly enhance the model's ability to discriminate between relevant and non-relevant items. To better understand the properties of the proposed hybrid loss, we compare it with several widely used ranking losses in the industry. The experiment results indicate that the hybrid loss consistently outperforms other alternatives, surpassing both its individual components, the sorting loss and the AM rank max loss. Moreover, our proposed AM rank max demonstrates superior performance compared to the original rank max loss and the soft max loss. We also conduct an ablation study on the distillation component and further compare softmax loss with other alternatives. It demonstrates the efficacy of transferring knowledge distillation. Among various loss function experimented for distillation, the softmax loss outperforms the other alternative losses. The softmax loss, being a listwise ranking loss, proved more adept at distilling the ranking model's capabilities compared to the weighted log loss, which essentially is a pointwise approach and exhibited suboptimal performance in learning the relative ranking distribution. In contrast, the pairwise log loss, focusing solely on pairwise ordering of ranking models' predictions without considering the relative proximity of predictions, exhibited overfitting to the ranking model's outputs. To conclude, this paper introduces the RankTower model, designed to enhance the performance of the two-tower model by effectively capturing bidirectional latent interactions between user and item. To ensure consistency with existing cascade ranking system, a hybrid loss function and full-stage sampling approach are integrated into the model's optimization framework. Comprehensive experiments demonstrate that RankTower significantly outperforms state-of-the-art pre-ranking models.